go on. That shortcut relies on the principle that a negative exponent in the numerator corresponds to a positive exponent in the denominator. For example, the x to the negative 2 in the numerator here, after some manipulations, became an x to the positive 2 in the denominator. Furthermore, a negative exponent in the denominator is equivalent to a positive exponent in the numerator. That's what happened when we had the y to the negative 5 in the denominator and translated into a y to the positive 5 in the numerator. Sometimes people like to talk about this principle by saying that you can pass a factor across the fraction bar by switching the sign of the exponent. That is, making a positive exponent negative or a negative exponent positive. Let's see how this principle gives us a shortcut for solving these two problems. In the first problem, 3x to the minus 2 over x to the 4, we can move the negative exponent in the numerator and make it a positive exponent in the denominator. So we get 3 over x to the 4 plus 2, or x to the 6th. In the second example, 4y cubed over y to the minus 5, we can change the y to the minus 5 in the denominator into a y to the 5 in the numerator and get our final answer of 4y to the 3 plus 5, or 8. We'll use this principle again in the next problems. In this example, notice that I have y's in the numerator and in the denominator, and also z's in the numerator and in the denominator. In order to simplify, I'm going to try to get all my y's either in the numerator or the denominator, and similarly for the z's. Since I have more y's in the denominator, let me move this y to the 3 downstairs and make it a y to the negative 3. I'm using the principle here that a positive exponent in the numerator corresponds to a negative exponent in the denominator. Now, since I have a positive exponent on z in the numerator and a negative exponent in the denominator, and I want to get rid of negative exponents, I'm going to pass the z's to the numerator. A z to the minus 2 in the denominator becomes a z to the plus 2 in the numerator. Notice that my number 7 doesn't move and when I do any of these manipulations because it doesn't have an exponent. And the exponent of negative 2, for example, only applies to the z, not to the 7. Now that I've got all my z's in the numerator and all my y's in the denominator, it's easy to clean this up using the product rule. And I have my simplified expression. In this last example, we have a complicated expression raised to a fractional power. I'm going to start by simplifying the expression inside the parentheses. I can bring all my y's downstairs and all my x's upstairs and get rid of negative exponents at the same time. In other words, I can rewrite this as 25 x to the 4th. I'll bring the y to the minus 5 downstairs and make it y to the 5th on the denominator. Bring the x to the minus 6 upstairs and make it x to the 6th in the numerator, and then I still have the y cubed on the denominator. All that's raised to the 3/2 power. Using the product rule, I can rewrite the expression on the inside of the parentheses as 25x to the 10th over y to the 8th. Recall that we're allowed to distribute an exponent across a product or across a quotient. When I distribute my 3/2 power, I get 25 to the 3/2 times x to the 10th to the 3/2 divided by y to the 8th to the 3/2. Now the power rule tells me when I have a power to a power, I get to multiply the exponents. So I can rewrite this as 25 to the 3/2 times x to the 10 times 3/2 over y to the 8 times 3/2. In other words, 25 to the 3/2 times x to the 15th over y to the 12th. Finally, I need to rewrite 25 to the 3 halves. Since 3 halves can be thought of as 3 times 1 half, or as 1 half times 3, I can write 25 to the 3 halves as 25 to the 3 times 1 half, or as 25 to the 1 half times 3. Well, using the power rule in reverse, I can think of this as 25 cubed to the 1 half, or as 25 to the 1 half cubed, since when I take a power to a power, I multiply the exponents. 25 cubed to the 1 half might be hard to evaluate, since 25 cubed is a huge number. But 25 to the 1 half is just the square root of 25. So I have the square root of 25 cubed, or 5 cubed, which is 125. Therefore, my original expression is going to be 125 x to the 15 over y to the 12th. In this video, we use the exponent rules to simplify complicated expressions. This video goes through a few tricks for simplifying expressions with radicals in them. Recall that this notation means the nth root of x. So this notation here means the cube root of 8, the number that when you cube it, you get 8. That number would be 2. When we write the root sign without a little number, that just means the square root, so the 2 is implied. In this case, the square root of 25 is 5, since 5 squared is 25. Let's start by reviewing some rules for radical expressions. First, if we have the radical of a product, we can rewrite that as the product of two radicals. For example, the square root of 9 times 16 is the same thing as the square root of 9 times the square root of 16. You can check that both of these evaluate to 12. Similarly, it's possible to distribute a radical sign across division. The radical of a divided by b is the same thing as the radical of a divided by the radical of b. For example, the cube root of 64 over 8 is the same thing as the cube root of 64 over the cube root of 8, and you can check that both of these evaluate to 2. You have to be a little bit careful, though, because it's not okay to distribute a radical sign across addition. In general, the nth root of a plus b is not equal to the nth root of a plus the nth root of b. And similarly, it's not okay to distribute a radical across subtraction. If you're ever in doubt, you can always check with simple examples. For example, the square root of 1 plus 1 is not the same thing as the square root of 1 plus the square root of 1. The right side evaluates to 1 plus 1 or 2, and the left side is square root of 2, an irrational number. The second expression, to show that that fails, I don't think it'll work to use the square root of 1 minus 1. It'll actually hold in that case, but I can show it's false by using, say, the square root of 2 minus 1, which does not equal the square root of 2 minus the square root of 1. You might notice that these rules for radicals, the ones that hold and the ones that don't hold, remind you of rules for exponents, and that's no coincidence, because radicals can be written in terms of exponents. For example, if we look at the first rule, we could rewrite this. The nth root of a times b is the same thing as the 1 over nth power. And by exponent rules, I can distribute an exponent across multiplication. And so this radical rule can be restated completely in terms of an exponent rule. Similarly, the second rule can be restated in terms of exponents as a over b to the 1 over n is equal to a to the 1 over n divided by b to the 1 over n. We can use the relationship between radicals and exponents to rewrite a to the m over n. A to the m over n is the same thing as a to the m, with the nth root taken,
It's also the same thing as the nth root of a, all taken to the mth power. To see why that's true, think about exponent rules. So a to the m over n is the same thing as a to the m taken to the 1 over nth power. That's because when we take a power to a power, we multiply exponents, and m times 1 over n is equal to m over n. But a 1 over nth power is the same thing as an nth root, and therefore this expression is the same thing as this expression, and that proves the first equivalence. The second equivalence can be proved similarly by writing a to the m over n as a to the 1 over n times m. Again, this works because when I take the power to the power, I multiply exponents. 1 over n times m is the same thing as m over n. But now, these two expressions are the same because the 1 over nth power is the same as the nth root. One mnemonic for remembering these relationships is flower over root. So flower is like power and root is like root. So that tells us we can write a fractional exponent. The m becomes the power and the n becomes the root in either of these two orders. Now let's use these rules in some examples. If we want to compute 25 to the negative 3/2 power, well, first I'll use my exponent rule to rewrite that negative exponent as 1 over 25 to the 3/2 power. Next, I'll use the power over root mnemonic to rewrite this as 25 to the 3rd power square rooted, or as 25 square rooted to the 3rd power. I wrote the 2's there for the square root for emphasis, but most of the time people will omit this and just write the square root without a little number there. Now I could use either of these two equivalent expressions to continue, but I'd rather use this one because it's easier to compute without a calculator. The square root of 25 is just 5. 5 cubed is 125. So my answer is 1 over 125. If I tried to compute the cube of 25 first, I'd get a huge number. In general, it's usually easier to compute the root before the power when you're working without a calculator. Now let's do an example simplifying a more complicated expression with exponents in it. I want to take the square root of all this stuff, and since I don't really like negative exponents, I'm first going to rewrite this as the square root of 60x squared y to the 6th over z to the 11th. So I'll change that negative exponent to a positive exponent by moving this factor to the denominator. Now, when you're asked to simplify a radical expression, that generally means to pull as much as possible out of the radical sign. To pull things out of the square root sign, I'm going to factor my numbers and try to rewrite everything in terms of squares as much as possible. Since the square root of a square, those two operations undo each other. So I'll show you what I mean. First, I'll factor 60. So 60 is going to be 2 squared times 3 times 5. And I'll just copy everything over for now. Now I'll break things up into squares as much as possible. So I've got a 2 squared times 3 times 5. I've already got an x squared. I'll write the y to the 6th as y squared times y squared times y squared. And I'll write the z to the 11th as z squared times z squared, I guess 5 times, 1, 2, 3, 4, 5, times 1 extra z. That should add up to z to the 11th if I add all those exponents together. Now I know that I can distribute my radical sign across multiplication and division, so I'll write this with a zillion different radicals here. And every time I see the square root of something squared, I can just cancel those square roots and the squares out and get what's left here. So after doing that cancellation, I get 2 times the square root of 3 times 5 times x times y times y times y over z times itself, I guess 5 times the square root of z. And now I can clean that up with exponents. I'll write that as the square root of 15 I guess 2 times the square root of 15